Hello, everybody. Welcome to a code deep dive for the American Wood Council National Design Specification, the 2018 edition. This is Building with Blitz, and we're going to start a series of code deep dives where we kind of dissect the layout of each code and what you're going to most commonly use each specification for. Well, I'll kind of give an example for that as we get into it. So let's go ahead and get started. So why should we care? The American Wood Council publishes these design specifications. The 2018 version is referenced, one, because the PE Civil Structural Exam, the code specification calls out this edition. I'm not sure if they have a more recent one. I wouldn't be surprised if they do, but some things kind of take a while to get adopted into the system, as well as the International Building Code. I know up until 2022, still use the 2018 version of the specification. So, with the IBC in mind, the NDS is the rule of the road for wood design and wood member analysis. But if there is a provision within the IBC that has a more conservative limit state, then you have to use that due to the code hierarchy. There could be some questions on the PE exam or throughout coursework where you kind of get a little bit of a gotcha. So you have to be careful to always check if you have it available, or if it's, during the PE exam it's available, but for coursework, if you have the IBC available, go ahead and check that just to make sure there's not any additional provision that would make your design invalid because it's no longer code compliant. So let's go ahead. The layout of the NDS, it's actually a pretty easy read when compared to most codes. Like the AISC 360 is, I think, a little bit harder to read. It's multiple hundreds of pages long, and it's just a little bit. I don't know. The NDS to me just reads easy compared to AISC. ACI 318, kind of the same way. It reads easier than that. So it's broken up primarily into kind of these groups. Chapters 1 through 10 of the provision really talk about member analysis and design, this meaning section analysis or design provisions and equations from chapter 3. That's where you're kind of thinking about flexure, shear, deflection criteria for bending members, compression members, kind of the same thing. How to design a section based on forces, where chapters 4 through 10, which I'll get into in a second, are kind of component specific, and I'll explain in a second what that means. Chapters 11 through 14 are going to be your fasteners and connections. This is anywhere from screws and nails to certain shear plate or truss connectors. And then chapters 15 and 16 I labeled as special conditions. This is because you're not really going to see a lot of this at least I haven't, in one graduate coursework. And I will say a lot of the wood design or wood analysis courses, while there might be a couple at a particular university as an elective, most of the time it's going to be a graduate level course. So to make note of that, the isn't really seen, and even with the PE Civil Structural Exam, you don't really touch on that because Chapter 15 is special loading conditions, and Chapter 16 is fire design of wood members. So given the scope of the exam and even kind of the scope of the coursework, unless there's like an advanced wood design, you're just trying to get the general layout of what's going on. So you're really not going to see a whole lot of quote special cases within those two kind of ideas. So chapters 4 through 6, this is kind of the typical member design. I say that because you have sawn lumber, glulam timber, and timber poles and piles. So I should say this to start. I mentioned previous chapter 3. That is kind of where you want to start once you have your reference design values. And this comes from each kind of type of member section. So for chapter 4, I have on the right here, you can see the adjustment factors for sawn lumber. And this is table 4.3.1. And this is where you're going to get your adjusted design values to then plug into the equations outlined in chapter 3. And I'll get into these factors in a minute, but this is common for every type of wood section. So for chapters 5, 6, 7, 8, 9, and 10, that reference design table is going to be whatever chapter number you're on, table 3.1. So for instance, chapter 9, wood structural panels, that's going to be table 9.3.1. So you really want to make note of that because these design values change quite a bit depending on your circumstances for your analysis. So like I was saying, 4 through 10 is kind of a member specific. So if you know that you're going to be using prefabricated wood eye joists, for example, you're going to want to hone in on chapter 7. And chapter 7 material does not always apply across chapters. So you have to pay attention to what you're doing. Glulam is a big example of this, where you would think, oh, glulam and sawn lumber, it's going to behave pretty similarly. And while that is true most of the time, from a kind of take a step back perspective on it, there are certain design values that do change due to the makeup of each member. So let's talk about these adjustment factors. And I called out for sawn lumber because one, they do change, or they can change depending on what chapter you're in. However, most of these are going to be pretty similar across different sections of wood members. So wet surface factor, CM, that is dependent on your environment condition. So if you have a wet environment or a high humidity environment, you're going to adjust accordingly. And that's shown in the NDS supplement, which I'll talk about in a second, because it is kind of species dependent on how, moisture is absorbed into the wood itself. Temperature factor, this is in chapter 2, because this does not change across each section. You're going to have, this can get you, I will say, because I'll take an example. So if your temperature ranges between 125 and 150 degrees Celsius, for compressive strength, you're going to reduce that number that you pull from the extra supplement by half. So if you're not careful about knowing your environment, and if you have a question that specifically calls out a temperature, it's pretty important to check that temperature factor. Less than 100 degrees, you're not going to adjust anything. But once you start getting over 100 degrees, you want to take a look at that. So the beam stability factor, this is in section 3.3.3 of the supplement or the specification. This is a flexure design property. Obviously, if we're designing beams, we're going to be flexure is most of the time going to be controlling. And so, what that is kind of similar to, if you're familiar with steel design, you want to have a stable beam, whereas this can get into kind of slenderness ratios and some torsional buckling, similar to steel. So this beam stability factor accounts for that. It is a little complicated. I will have an example of how to calculate beam stability in another video, along with all of these other factors. But this is just kind of an overview of the code. But for example, for this beam stability factor, you have to consider the E prime minimum. This is you get this from the supplement, but it's the minimum modulus of elasticity for that particular species. And then you'll run that through the adjustment factors in the table, as well as bending adjustment factor. While you have to leave some factors off, you have to, you got a lot of pieces to the puzzle, and this is just for one factor. And you can experience a large reduction in the design value from this. So you can't really just kind of leave it at 1.0. You have to work it out, and you'll kind of get a feel for kind of the effective length of what the effective length, and then what your other factors are and how they're going to play a role in the stability factor. And I don't know, you could probably get a feel for it and then guess, say, hey, this is going to be pretty close to a 0.95 reduction. So I'll go ahead and do that without having to run all of these formulas. So for the size factor CF, this is found in section 4.3.6, and it's noted to be in section 4 because it is dependent on sawn lumber. I do know glulam has similar, but still different size factors. So this depends on kind of the depth of the member. If you, for instance, if you have a deeper member, say at 12 inches versus a more narrow or a shorter, you're going to have a different bending stress because you are squaring or cubing that height to resist the moment, or squaring if you're using section modulus. So size factor is important to use. However, you'll kind of get a feel for it like a regular 2x4 is not going to have any reduction. So flat use factor, moving on, this is thinking about how the member is oriented along its strong or weak axis. So if you have for instance, a 2x4 on the wide side, the 4-inch facing down, or 4-inch in the Y plane, you're going to have a reduction in the overall strength because you're not using the member to its full kind of capacity by putting it on its flat side. And so this factor kind of takes that into account. Moving on to incising factor, I will say this can get you, but you'll know if, specifically talking about coursework or licensure exams, you'll know if the section is incised or not because it'll call it out in the problem. But it can bite you because looking at it for bending strength, if it's incised, you take a reduction of 0.8. So say you have 1,000 psi bending strength, you're losing 200 psi of strength just by that being incised. And if you don't take that into account, 200 psi is a lot if you start talking about getting close to the utilization ratio of that section. So you really want to be careful that you're not taking that into account for a conservative design. Repetitive member factor, this one is interesting, and it's more for layout of, you're not going to get this for an individual section, like a one beam per se, because it's focused on the layout of the, like a wall, for instance. So if you have, um, member spacing, I want to say no. So 4.3.9 calls it out as not more than 24 inches on center, along with some other criteria. You're going to increase the strength of that particular section by a factor of 1.15. So you'll see, especially in residential, that's why a lot of wood studs are spaced at 16 inches on center, because you're allowed to increase strength of each beam or column by taking that layout. So again, for a particular like one-off question, like, hey, analyze this glulam beam with X loading, you're not going to take member factor into account. But if you have a question of, hey, this wall is supporting, a load of 1 kip per linear foot, and studs are spaced 16 inches on center, you then will take that into account. Column stability factor, very similar to beam stability factor, except for it's a column. So it's to take into account some type of torsional buckling, or buckling based on slenderness ratios. And so you can expect kind of a rigorous calculation, because it is very similar. It really only swaps out the bending design value for compression. So if you're good at one, you'll inherently be good at the other, because they're very, very similar. The buckling stiffness factor is in the special design considerations. For section 4.4 is special design considerations. 4.4.2 is wood trusses. So if you're designing wood trusses, you're going to be using this. However, just for a one-off beam or a wall or anything, like I said, that's not a truss, you don't have to take this into account. So those are kind of all the adjustment factors, regardless of design methodology. But now there's also some adjustment factors for whether you're going to use allowable stress design or load resistance factor design. I will say I'm a proponent of LRFD in about every other case but wood. So this is because, one, there's 3 factors to LRFD versus ASD's 1, and that's the load duration factor of CD. So, one, that's less things to worry about, and you're pretty set. The table 2.3.2 outlines if you have, live load, you're going to take a reduction of, say, I don't think it is, but 0.9, for example. Whereas LRFD, you have format conversion factor, resistance factor, and time effect. So the resistance factor, think about just like regular LRFD, take a 0.75 reduction or 0.8, 0.9, et cetera, depending on what you're designing. Whereas ASD, you just take it flat off the top. I'm going to have 90% of this bending value, and I don't have to do anything else. So that is something to look at. I know a lot. I mean, I learned LRFD in school up until I got to my wood design class. And then I learned and actually applied ASD principles. And I will say, I think it's much easier. So moving on into chapters 11 and 12, the mechanical connections of chapter 11 and then the dowel type fasteners of chapter 12 is kind of the bread and butter. So for coursework or for licensure exams, I would be surprised if you saw anything outside of these 2 chapters. They read very similar to a section design chapter. So if you can, utilize those adjustment factor tables and know exactly what value you're trying to get out of those tables, it's very simple. And I will note that the connections chapters do not use the supplement, so it's all within the provision, which kind of one less book or code to flip through to get those values. Chapters 13, split ring and shear plate connectors, and 14, timber rivets. A little bit more specialized, but again, the way the NDS is set up, if you can read one chapter, you can read them all. Just because you're looking for the design table or the adjustment factor table, and then hey, does this circumstance of my design meet X, Y, or Z to apply that factor? And then you either do or don't. So the supplement is when you order the specification, you get the supplement. So, and it's honestly necessary. You can't really do wood design without it. So chapter 3 is the section properties. This is where you're going to get the geometric properties of a section. Like, for instance, a 2x4 is not exactly 2 inches by 4 inches. It's 1.5 by 3.5. And so instead of having to calculate, moment of inertia relative to the x-axis, or the section modulus relative to the x-axis, it gives you those values within chapter 3. And table 1A is member designations. This is whether it be a board, a dimension lumber, or a timber. This can affect how you approach a problem. If, for instance, you have an issue or a problem within an exam that is, hey, use a southern pine timber. So you're not going to be pulling from a 2x4 design properties, because a timber has certain geometric properties of depth and width that make it a timber. So you're going to be using a different reference design value table. So to mention the reference design value table, table 4B is southern pine only. So if you have a problem or you're designing something that is not southern pine, then you can use table 4A. But if it expressly calls out a southern pine, 2x8, you cannot use table 4A or any other table. I say that, but if it meets certain geometric properties, but for 2x8, for example, you're going to use table 4B. You're not going to use table 4A. So 4A is every species except for southern pine. So you have to be careful of if you have a question on it, what it is asking, because it will change your design value or your PSI rating by up to 200 PSI. So that's a pretty important value to take a look at. So here's an example. So a 2x4 southern pine, say bending. We're designing a beam, and we want to say, hey, what is the bending stress given my circumstance? So we first get the value of the F of the bending stress from table 4B. This is 1500 PSI. We take that 1500 PSI and multiply it out by every factor that is applicable to our analysis or our design. So I typically use ASD. So I know I'm going to be multiplying it by a load duration factor. And the rest of them are circumstantial. So wet service, if you meet the criteria, you have to multiply it by that factor. Temperature, if it's above 100 degrees, you want to take a look at it. Beam stability factor, you're going to multiply that every time. and so on. So you get all of these, and I will say on the right, you do not use the LRFD if you're not designing that way. So you would, in my instance, I would just use ASD. So what does this mean for the FE&P exam? Not really a whole lot for the FE exam because you don't really get into material specific design outside of steel and concrete. Again, because the FE is really meant to be kind of an undergraduate licensure, or you're still in school licensure exam to get that EI or EIT. So you're not really diving into kind of the specialty. Whereas the PE exam, if you're doing the civil structural, of course, there's there could be up to spitballing. I can't give, nor do I know exact numbers, but spitballing. Say you have 5 wood design connection or wood design or wood connection design questions. So because it is considered to be specialized, I would say that the questions you get are not going to be crazy in depth. It might just be a code interpretation question, which can be easy layup questions if you know how to read the NDS. That's kind of why I'm making this video, so that way you can get accustomed to the flow of it and say, hey, I have a saw and lumber question. You know, what is X factor for a saw and lumber? You know exactly where to find that. And we will have example problems later on of specific kind of design or analysis questions that will go through what each factor and how to apply it, even though it's kind of common sense because it outlines it in the code. But to see an example problem, I think would be a big help. So moving forward, the American Wood Council also has a special provision for basically seismic and wind provisions. Because seismic and wind can get complicated, as I've said and will continue to say, there are certain parameters and provisions you have to take when designing, say, a diaphragm for a wind provision. And certain connectors and sheathing thicknesses that are not typically outlined in the NDS, but are referenced in the SDPWS. And this is the 2015 version that we'll talk about. So that'll be coming up. So I want to thank you, everybody. And if you have any question or want to see anything in specific, please let me know via comment or email. And yeah, thanks again and have a good rest of the day.